We're continuing our discussion of Chapter 3 Logic, and today we're going to talk about truth tables. This is Section 3.3, Truth Tables for Negation, Conjunction, and Disjunction. The objectives are to use the definitions of negation, conjunction, and disjunction to construct truth tables and determine the truth value of a compound statement for a specific case. Remember that negation or not is the opposite truth value from a statement. So if P is true, not P is false. If P is false, not P is true, as shown in this. This is a truth table. For conjunctions, and, they're only true when both statements are true. So if you've got that P is true and Q is true, the conjunction P and Q is true. For all other instances where one or both are false, then the P and Q would be false. Disjunction, or. These are only false when both statements are false. So again, looking at this truth table, we have true, true, which is true for the conjunction, but the disjunction. True, false, which again is true. False, true, which is true. So this disjunction of P or Q is only false when both statements are false. Example 1, we're going to use the definitions of negation, conjunction, and disjunction. So we're letting P and Q represent these statements. P is 10 is greater than 4, and Q is 3 is less than 5. So we want to determine the truth value of each of these statements. P and Q, well, 10 is greater than 4, 3 is less than 5. So the truth value for the conjunction is true. For not P and Q, since P is true, not P is false. So going back to the previous screens, we see that the conjunction, not P and Q, would be false because one of the statements is false. Continuing with C, P or not Q. Okay, P, which is 10 is greater than 4 is true, and Q, as it is also true, but not Q is false. A disjunction is false only when both components are false. So since P is true and not Q is false, only one component is false, and this is a true statement. For D, not P or not Q. Kind of going back to C and including it in D. P is true, so not P would be false. We already saw in C that not Q is false. So since both of these are false, then we would have that the disjunction is also false. Example 2, constructing truth tables. We want to construct a truth table for not P and Q. So the first step is to list the simple statements on the top and show all the possible truth values. So we have P and we have Q. So we list P and the possible values would be true, true, false, false. For Q, it would be true, false, true, false. Or you could do it true, true, false, false, like you do with P. It doesn't really matter. Then we want to make a column for P and Q and fill in the truth values. Remember that for and, both of these statements or components have to be true. So for P and Q, only the first one, where P and Q are true, would be true. All the others are false. Now we want to construct one more column that shows not P and Q. So not P and Q would be the opposite of P and Q. So this tells us that the statement is false only when both P and Q are true. So that would be this first one. All the remaining ones are true. For example, Harvard is a college, true. Yale is a college, true. Not P and Q. It is not true that Harvard and Yale are colleges. A compound statement that is always true is called a tautology. Is this a tautology? No, because it can be false. Example 3, we're going to construct a truth table. This one's a little more complicated, but if you go about it the same way, you'll be fine. We see that we're using P and Q again. So we will list P and all the possible values. We list Q and all the possible values. We have not P, and so we're going to find not P, which is the negation of P, as you can see in the next column. Okay, we are going to deal with the part inside the parentheses, if you recall from a previous section. So we're going to do not P or Q. Okay, so not P or Q. One of these is true for the first one, true and false, so we get true. For the next line, both are false, so it's false. And for the remaining two, it would be true because both of them, not P and Q, are true, or not P is true and Q is false. The next part is not Q. Well, we go back to our column that has Q. This is just the negation of Q. And finally, we're ready to do the AND. Remember that for AND, both parts have to be true for the compound statement to be true. So we're going to look at it's actually the third column and the fourth column. Both of them have to be true or the compound statement is going to be false. So for the first line, it's going to be false. For the second line, it's going to be false. For the third line, it's going to be false. For the last line, both are true, so it's going to be true. Notice that if we just have P and Q, two instances, then we're going to have 4 cases that we deal with. On the next one, we're going to have 8 cases because we have 3 simple statements, P, Q, and R. So from this table, you see that there are 8 different true-false combinations for compound statements consisting of 3 simple statements. Example 4. Constructing a truth table with 8 statements or 8 cases. Now this is the same way that we did before, it's just a little more complicated. A is I study hard and ace the final, or I fail the course. B, suppose that you study hard, you do not ace the final, and you fail the course. Under these conditions, is this compound statement true or false? So to start out, we're going to represent our statements as follows. P is going to be I study hard, which is the first part of A. Q is I ace the final, and R is I fail the course. So we take that directly from the statement in A. We're going to write the statement in symbolic form. So P, I study hard, and I ace the final. There's a comma, so we include those first 2 things inside parentheses, or I fail the course, which is R. So the completed table is going to look like this. You list P, Q, and R with all of the different 8 combinations you can have for them. Then you're going to look at P and Q, which is the part in parentheses that goes first. That is going to be your second column. Remember, for P and Q, both parts have to be true. So the first line is true, the second line is true. The remaining lines are false because either P is true and Q is false, or P is false and true and Q is true. So we've got P and Q in the second column. That leaves us with the entire compound statement. So we're going to add, for the last column, the part in parentheses, P and Q, or R. Okay, now remember what we said before. The disjunction is false only if P and Q, which is this column, is false and R is false. So we look at R and P and Q. Okay, for the first line, they're both true. For the second line, one is true. For the third line, one is true. For the fourth line, both are false. So this is an instance where they're false. For the next line, R is true, P and Q is false, so it's going to be true. Next line, both are false, so it's going to be false. For the next line, R is true and P and Q is false, so it's going to be true since one of them is true. And then for the last one, both are false, and so it'll be false. So the statement is true. Now we're going to determine truth values for specific cases. We can determine the truth value of a compound statement for a specific case in which the truth values of the simple statements are known without constructing an entire truth table. You can, but you don't have to. You're going to substitute the truth values of the simple statements into the symbolic form of the compound statement and use the appropriate definitions to determine the truth value of the compound statement. Sounds a little complicated, but bear with me. So example 5, determining the truth value of a compound statement. For this one, we have a bar graph. And the bar graph shows the distribution of looks for American men and women, ranging from homely to strikingly attractive. And this is definitely not politically correct. But anyhow, this is our bar graph. We're going to use the information in the bar graph to determine the truth value of this statement. It is not true that 1% of American men are homely and more than half are average, or it is not true that 5% of American women are strikingly attractive. So we begin by assigning letters to each simple statement, and we use the graph to determine whether these statements are true or false. Okay, so we're going to let P be 1% of American men are homely. Q, more than half of American men are average looking. And R, 5% of American women are strikingly attractive. P, Q, and R represent the simple statements in the problem that we're trying to find. So for P, if we look back at the graph, 1% of American men are homely. This is true. For Q, more than half of American men are average looking. This is true. 59% of American men are average, which is more than half. For R, 5% of American women are strikingly attractive. This statement is false because, according to the graph, it's 3% rather than 5%. So P is true, Q is true, R is false. We're going to substitute the truth values of P, Q, and R that we obtained from the bar graph to determine the truth value. So we have written the compound statement in symbolic form. Notice the parentheses. We're substituting the truth value obtained from the graph. So we found that P is true, Q is true, R is false. Okay, we look at the part in parentheses first. That's an and. If both parts of the and are true, then it's true. So the part inside the parentheses is true. We still have that R is false. Okay, but not T, not true, would be false. So we have false or true. Well, remember that for the disjunction is true if either part is true. So if we replace this F or false or T, true, with T, then this is true because at least one part is true. We conclude that the given statement is true. And that concludes this section.